what I mean to say is that this line, which forms angle theta 0 to the x-axis, is described by the equation theta equals theta 0. In the first equation, r equals r. Theta is arbitrary. Well, not exactly arbitrary. As we saw, it should really be between 0 and 2 pi. But in this equation, r is arbitrary. Both positive and negative. So in fact, this is the reason why we introduce this rule, which may look strange at first sight. Because remember, as I said at the beginning, strictly speaking, r should be non-negative. If we follow the definition of polar coordinates, in which r is just a distance, so it has to be non-negative. But if we were to adopt this point of view, then the equation theta equals theta 0 would actually correspond not to this entire line, but only to half a line, a kind of array which goes from the origin to infinity. Which is fine, it's a fine geometric object and so on its own right. But if we adopt this rule, if we allow r to be negative, and we plot points with negative r's the way we just discussed, then not only half a line will be represented in this equation, which will correspond to positive r, but also the entire line, the second half a line, will correspond to negative values of r. So this is the advantage of this rule, that if we follow this rule, then we have a nice representation by an equation of the entire line like this, and not just half a line. Okay, what else can we learn from equations with polar coordinates? So I want to look at a couple of more complicated examples. I'm sorry? What is? Arbitrary. Why is it arbitrary? The question is, why did I say r is arbitrary? Because when I write this equation, r is nowhere to be found in this equation, right? So the meaning of this equation is, we look at all points on the plane whose theta coordinate is fixed. It is equal to theta 0. Theta 0 could be any number between 0 and 2 pi, like pi over 4, pi over 3, whatever you want. Any real number between 0 and 2 pi. So theta is fixed, but r is arbitrary. When I write this equation, because this equation does not involve r, this equation means that r can take arbitrary values within the allowed range. The allowed range initially was stipulated to be r greater than 0, maybe r greater than or equal to 0. But eventually we decided that we'll allow negative values of r. So that's why, well, actually maybe it's better to write like this. And on this line, we actually see the part corresponding to r greater than 0, the part corresponding to r less than 0, and there's one point which corresponds to r equals 0. Likewise, when I write this equation, what I'm saying is that I look at all points on the plane for which the r coordinate is fixed. It's equal to some number, capital R, which could be 5, 10, 13, whatever you want. But because theta does not appear in the equation, it means that theta is arbitrary within the allowed range of theta. And what is allowed range? The allowed range here is from 0 to 2 pi. So that's the meaning of this. Okay. Now let's look at more complicated examples. So 3, r equals cosine theta. So again, a perfectly legitimate equation involving the two polar coordinates r and theta. In other words, we're looking at all points on the plane for which, whose r and theta coordinates are constrained by this relation. It's like writing in the case of Cartesian coordinates, writing an equation x squared plus y squared equals 1. It's one equation involving our two variables x and y. Likewise, this is also one equation involving our two variables r and theta. We have now switched to the polar coordinate system. So the question you can be asked is to draw this. To see what this curve represents. And in this case, actually, it's easier to understand what this curve represents by switching back to the Cartesian coordinates. This is not to say that this equation is useless. In fact, on the contrary, you can then use this equation to compute various things about the curve, as opposed to the equation in Cartesian coordinates. But first, we want to visualize that. What does it mean? And here, we have to look back at the dictionary, at the formulas expressing the polar coordinates in terms of the Cartesian coordinates. And so we could just write r square root of x squared plus y squared equals cosine theta, and then, but we know tangent theta, so it's a little bit tricky, so it's not clear how do we get a good formula. Okay, so it doesn't work. So let's look instead at the geometry of this picture. So then let's see what cosine is. Cosine theta, what is it in terms of x and y? Well, it's better to say not in terms of x and y, but in terms of x and r, right? Because this length is x, this length is y, and this length is r. So the cosine theta is the ratio of this side to this side. That's why cosine theta is x divided by r. Now let's substitute this in this formula. So we get r equals x divided by r. And now we can multiply both sides by r. So we get r squared equals x. Okay? And now is a good time to express r squared in terms of x and y. Because remember, r squared is x squared plus y squared. So we substitute here, and so the result is x squared plus y squared equals x. And this is already much more manageable. Let's take x to the left-hand side. And let's complete the square. We can write x squared minus 2 times 1/2, 2 times x times 1/2, plus 1/2 squared. And then, so I introduce an additional term, 1/2 squared, which is 1/4, on this side, and to compensate for this, I also introduce it on the right-hand side, so that I get a true equality. And of course, I shouldn't forget y squared as well. You see, so I just put two additional terms on the left and right-hand side, which is 1/2 squared. But if I do that, then the first three terms combine into a square. The first three terms give you x minus 1/2 squared plus y squared equals 1/2. And then the end result is already an equation which is familiar. The end result is x minus, let me use a different chalk. So we get x minus 1/2 squared plus y squared equals, okay? Yes? Okay. This was by way of making things easier for you, but I guess maybe I didn't achieve that goal. 2 times 1/2 is 1, right? So that's why I wanted to write it, I wanted to use the formula a plus b squared is equal to a squared plus 2ab plus b squared. And I had x, and I want to have something which is twice. So that's why I wrote x as 2 times x times 1/2. Does that make sense? and then I saw that, so that means x is a and b is 1/2, and then I put b squared, which is 1/2 squared, which I also introduced on the other side. Completing square. That's right. That's all it is. So I'm not cheating. It's all legitimate. But yeah, but please check, because sometimes I can make a mistake. It works out. So that's the equation we get. And now we can draw it, because you see, of course, we're more familiar with the curve x squared plus y squared is 1/2 squared. That curve is a circle, of course, of radius 1/2. Let me make it bigger. 1/2. What's the difference between this equation and this equation? We just shift by 1/2, right? So what does it mean geometrically? Geometrically, it means that we shifted to the right by 1/2. Why to the right? Because, for example, here the point with x equals 0 will correspond to the point with x equals 1/2, so that this whole thing will become 0. So shifting x by minus 1/2 means shifting everything to the right by 1/2. And when we shift everything to the right by 1/2, it means that the center of the circle, which used to be the origin, now becomes this point, whereas this point now becomes this point. And so it's actually a circle which looks like this. Okay? So this is the circle which is represented by this equation. Which is kind of neat, because if you want to write it in Cartesian coordinates, you get this equation, which is not too bad, but certainly this looks much more economical in some sense. And so for the purposes of some calculations, it could be very useful. Okay. What else can we do? Let's do a small variation on this problem. So that would be number 4. A small variation would be r equals cosine of 2 theta. So see, now we can't really get away with a simple formula for it, because here we use the fact that cosine theta has such a nice expression. You can still try. Cosine theta is cosine squared of theta minus sine squared of theta. So then you can rewrite cosine squared and sine squared, but you'll get something really complicated. So when you get to a situation like this, where you can't really rewrite it in a nice way by using the Cartesian coordinate system, you need to try to just kind of understand qualitatively what this curve looks like. And to do that, we should look at this equation as if r and theta were Cartesian coordinates in some other world. R and theta are Cartesian coordinates, right? So I'll kind of, in a pink world, this will be like Cartesian coordinates, right? So we'll just draw theta and r, and we'll draw this graph in r and theta, and then we'll try to see what it means in our world, which is like the yellow world for now. Okay? So what this is just a cosine function, except the period of the cosine function is now shrunk to pi instead of 2 pi. Right? Because already when theta is pi, you get cosine of 2 pi, so you're back to square 1, back to 0. So cosine looks like this. At 0, it's 1, and then it becomes 0 at pi over 2, then it becomes negative 1, then it becomes 0 at 3 pi over 2, and then it goes back to 1 at 2 pi. And then it continues like this. Right? But now we have to realize that normally if it were just cosine function, normally if it were cosine theta, this would be pi over 2. But because it's 2 theta, it's going to be pi over 4. And this will be pi over, normally it would be pi, but now it's pi over 2. And this is like 3 pi over 4. This is pi, and then it continues like this. So for example, at 5 pi over 4, it's going to reach 0 again, and so on. And now we would like to plot this on the plane where r and theta are polar coordinates, at least qualitatively, to get sort of qualitative understanding of what it looks like. So we just have to see what the points here correspond to on this picture. The first point is a point when theta is 0 and r is 1, right? So it's this point in which r is 1 and theta is 0. Let's plot it on this graph now, on this plane. So theta is 0, which means that we are on the x-axis. All points on the x-axis have theta equals 0, right? Because remember, theta is supposed to be the angle with the x-axis. So if theta is 0, it means you are on the x-axis. So you are on the x-axis, and the distance is 1. So you start here. That's your point. Or even to make it nicer, let's start here. That's our point. That's 1. What happens next? What happens next is we are increasing the angle from 0 to pi over 4. What is pi over 4? Pi over 4 is sort of this bisector. That's pi over 4. So when we reach pi over 4, r becomes 0. R becomes 0. And r equals 0, no matter what theta is, as we discussed, the origin. So we start here, and then the angle should increase. We should go from theta equals 0 to theta equals pi over 4. But at the same time, r is going to decrease until it becomes 0. So this is going to look like this, roughly. Because what else can it look like? You see, that's the point. I mean, it's a qualitative picture. I'm not insisting that I know exactly. There's no other way to represent it like this. If you try to write it in terms of Cartesian coordinates, you're getting nowhere. You're going to get a very complicated expression, which is not going to help you. So we can only study it qualitatively, and that's what it looks like. And now we continue. But see, what happens now is that r is a theta. Sorry, theta goes from pi over 4 to pi over 2, but r becomes negative. That's where our rule becomes really handy, because if we were, how should I say, too rigid, and said, no, r has to be positive, and we don't accept any negative values, we would have to say that this part is not acceptable. We can only look at the picture in this range, and so on, but not here. And what this would mean is that we would not be able to represent some very nice pictures by using polar coordinates. But because we've been flexible, and we said, we will accept negative r's, but following a particular rule, which we discussed, then we'll be able to actually draw the whole thing. And so what this is going to look like is that now pi is supposed to go from pi over 4 to pi over 2, but r becomes negative. R becoming negative means that we take the absolute value of r, but we shift the angle by pi. So that means that in the next segment, on this segment, we look at theta from pi over 4 plus pi to pi over 2 plus pi, right? So where is that? This is pi over 4. Pi over 4 plus pi is this, right? And pi over 2 plus pi is this. So it's going to go in such a way that r is going to go to 1 again, to negative 1, but then we have to take the absolute value, so it's going to be like this. Now it becomes positive. Oh, sorry, it still stays negative, and it continues to 3 pi over 4, and that's like this. So see, this segment is this segment is this, this segment is this, and I think now you can probably already guess what it's going to look like. It's going to be like this. That's right, like this, and then it goes like this. Huh? It's not so bad, huh? All right. Like this. A good thing to chew on over the long weekend. So there is one more thing which we need to discuss, which is the formula for the surface area for polar curves. But it's fairly straightforward. I'll just write the answer. Hold on. We still have 3 minutes, okay? So the formula for the area, which is 1/2 r squared d theta. And that's for a picture which you get by taking a segment, by taking a sector in on the plane, which is bounded by the curve and by the lines theta equals alpha and theta equals beta. The way you derive this formula is exactly the same. What you need to know is the same as the method which we use to understand arc length and surface areas for surfaces of revolution. And the method is to break it into small sectors and evaluate the approximate area of each small sector. And that's something you can read about in the book. It's very straightforward. Now, I want to end with two announcements. The first announcement is that, as you know, the first homework assignment is due on Wednesday because Monday is Labor Day. You turn your homework to at your sections, to your GSIs, to your TAs, all right, on Wednesdays. Now, on Wednesday night, after all the sections are over, I will post the solutions to all the homework problems in the set on the BSpace page online, okay? That's the first announcement. And the second announcement about my office hours. Normally, my office hours are supposed to be in my office in Evans Hall, but I think we're lucky that there is nobody, at least in the first two lectures. After the first two lectures, there was nobody here, so we'll just hold office hours here, in this room, from 5 to 6:30, all right? So I'll let you go. Have a good weekend.